Hello everyone, welcome to the Spintangle. Today we are starting a very new quantum statistics. Statistical mechanics is mainly distributed in three branches, okay, in which we discuss Maxwell Boltzmann statistics. This is not quantum statistics, okay, this is only statistics. Only statistics is distributed among three type of statistics: Maxwell Boltzmann statistics, and here it is a say Bose-Einstein statistics. This is in the name of our Satyendranath Bose, okay, Bose-Einstein statistics, and another statistics is called Fermi-Dirac statistics, okay, Enrico Fermi and Paul Dirac, okay, and this is J.C. Maxwell and Boltzmann, Ludwig Boltzmann, I think his name is Ludwig Boltzmann. So this statistics is called classical statistics, okay. This is a completely classical analogy in which the particles are treated as classical particles, and we know the classical particles are distinguishable particles also, okay. Therefore these particles are treated as individual distinguishable particles having distinct wave functions, okay. But in case of these two statistics, say this one is the Bose-Einstein statistics and this one is the Fermi-Dirac statistics. These Bose-Einstein statistics and Fermi-Dirac statistics are called quantum statistics. Why they are quantum statistics? Because in case of the particles are identical and indistinguishable, okay. The particles are identical and indistinguishable in both cases. So I am writing this thing identical in this case also. Identical particles, okay, identical particles means same looking particles, okay, and this is in case of Fermi-Dirac particles, all the particles are also identical particles, and indistinguishable particles, okay, indistinguishable. I am not writing it carefully, so you know thing in this thing, okay, indistinguishable. In the very I think in the very introductory lecture of the statistical mechanics, I have given a rough idea about the statistics, okay, indistinguishable. So go through the lectures if you have not gone yet. Therefore I advise you to go through this lecture, okay. So Bose-Einstein statistics. So what is the basic difference between Bose-Einstein and Fermi-Dirac statistics? They are both quantum statistics, okay? They are both quantum statistics. But what is the basic difference? The Bose-Einstein statistics have particles having integral spin particles, okay. That means spin 0, 1, 2, 3, not fractional spin actually, okay. In case of Fermi-Dirac particles, the are called odd integral spin, okay, mainly half integral spin, okay, odd integral spin. Odd integral means therefore no integers, okay. That means the particles can have spin value half or 3/2, 5/2, okay. So whatever it is, these are the theoretical particles that we do not deal in our natural sciences, okay. So these are, so example of Bose-Einstein particles are so called bosons, okay. The particles obeying Bose-Einstein statistics, we call the particle name as boson, okay. What are bosons? Say photon is a boson, okay. Say graviton is a boson. Photon has spin 1, graviton has spin, I think, spin 2, okay. Say Higgs boson is a boson. Higgs boson, I don't know. Higgs boson has, I think Higgs boson has spin 0, I think so, not sure, check it on Google, okay. And these particles are called fermions. These particles are called fermions. The particle obeying Fermi-Dirac statistics are called fermions. I am giving some example of fermions. Say electron is a fermion, electron is a fermion, say proton is a fermion, and also neutron is a fermion, okay, because electron has spin half, photon has spin half, proton has spin half, neutron has spin half, and that's all, okay. These are called boson and these are called fermions. So this is the basic differences between these three statistics, in which one statistics is called classical statistics and the rest of the other statistics are called quantum statistics, in which we will be discussing elaborately. Okay, so this is the basic outline of today's lecture. So now move on to the next topic. Okay, say before going to the quantum statistics very deeply, I am giving an introduction to the term called distribution function. What is distribution function? A non-mathematical analogy. Okay, distribution function. I'm giving a non-mathematical because this is a competitive platform, competitive examination platform, in which I'll not discuss more elaborately the what the distribution function and from where the distribution function is coming from. Okay, so distribution function, a non-mathematical treatment of distribution function. I'm writing this non-mathematical. Okay, I'm writing the distribution function directly. Distribution function in statistical mechanics is given as f of e1 ei, sorry, f of ei equals to what? This is the ni upon gi. This is the number of particles in ith state, and this is the degeneracy of the ei energy level. Say you have an energy level. I'm just giving, just wait. You have an energy level named ei. Okay, this is the ith energy state. In ith energy state, the degeneracy of the ith energy state is what? Gi. Say this is degenerate. Okay, this is the degenerate. Or in case of non-degenerate, you can put here 1. Okay, in case of non-degenerate. So here you have to put particles. These are the particles. These are the particles. These particles are how many number of particles? Say ni number of particles. Okay, ni number of particles. Here ei energy level and gi is the degeneracy. So the ratio of number of particles in a particular state to the ratio of the degeneracy of the state is called distribution function. Okay, so let's move on to the let me change the ink. Okay. Distribution, the general distribution function is given by 1 upon e to the power alpha plus beta ei plus some constant, say it is h. Okay, say it is h or whatever it is, k, give it k. Okay, so the basic difference between the basic definition, I'm giving the definition, or what do you understand by this distribution function term, is distribution function represents, I'm writing this thing, distribution function represents the probability that the particle will be found in EIth state. Okay, EIth energy state. You can write this thing as energy state. It is sometimes called as occupation number also. Okay, occupation number. Okay, this is what we call the distribution function, but you do not have to write this distribution function like this. Okay, I am moving to directly to the particular distribution function that you have to remember. Okay, so what is the distribution function? In case of distribution function, I am labeling first the individual statistics as follows. Say this is the in case of MB statistics. You have to remember this thing for your competitive purpose. Okay, I am not giving the detailed mathematical treatment of this thing. You have to go through the book, or you can join the graduation classes of our. Okay, so in the I think in the 6th semester, statistical mechanics will be discussed. Okay, so Maxwell-Boltzmann statistics, here it is a BOSE statistics, and here it is a Fermi-Dirac statistics. Okay, I'll write one thing, that Fermi-Dirac, in case of the difference of Fermi-Dirac and Bose-Einstein, that Bose-Einstein do not wait for the Pauli's exclusion principle. Okay, it does not obey the Pauli's exclusion principle, and Fermi-Dirac statistics obey Pauli's exclusion principle. Okay, so let's move on to the general format of the occupation number of each statistics. So what is the occupation number of MB statistics? MB statistics, the distribution function is given by FEI is equal to 1 upon e to the power alpha plus beta EI. Okay, where alpha is a constant, where alpha is a not alpha is a constant, but alpha has some value. Okay, alpha has some value, and beta is what I'm writing this thing. Beta is equals to 1 upon kt, and alpha is basically alpha is written as mu upon kt, where mu is what? Mu is chemical potential. Okay, chemical potential. Okay, at equilibrium the value of this chemical potential becomes 0, and in every non-equilibrium case this mu has some value. Okay, this is the distribution function that you have to remember for Maxwell-Boltzmann statistics. Okay, now I'm moving on to the Bose-Einstein statistics. The distribution function in case of Bose-Einstein statistics is given by f of EI equals to 1 upon, say it is Bose-Einstein, therefore e to the power alpha plus beta EI, there will be a minus sign. Okay, there will be a minus sign, and the value of H will be what? H equals to 1 here. Okay, H equals to minus 1. I'm giving H equals to minus 1 here, and okay, this is the distribution function that you have to remember for in case of Bose-Einstein statistics. So in case of Fermi-Dirac statistics, what you have to do, say it is f of EI equals to 1 upon e to the power alpha plus beta EI, and here will be a plus term. Okay, this is in case of Fermi-Dirac statistics. So you have to remember these three formulas. Okay, for your further for your discussions. Okay, so I'm moving to our topic today. Okay, say this is called the ideal Bose-Einstein gas. I am directly going to the Bose-Einstein statistics. Okay, what is our Bose-Einstein ideal Bose-Einstein gas? Okay, what is a Bose-Einstein gas? A system, consider a system, say this is a system that is filled with a gas, and the particle of the gas are bosons. Okay, these are what? These particles are bosons. Okay, so what we can write about this system, that a system of bosons. Okay, what are bosons? Bosons are particle having spin 0, 1, 2, 3 or integral spin. Okay, that's all. This is so. What does the ideal mean? Okay, Bose-Einstein gas means boson gas. Okay, boson gas or photon gas, whatever it is. And what does the ideal means? Do you know what ideal gas means? Ideal means the particle, one particle, say, do not interact with any other particle. Okay, that means the interaction potential is 0. The interaction potential is what? 0, because if this particle is here and the potential caused by this is spreaded over this region, and a second particle enters this region, this second particle will be affected by this thing, and and this is not allowed in case of ideal gas. This is in case of real gas. Okay, so in case of ideal conditions, this interaction potential is taken to be 0. Say this is V equals to 0. If this interaction potential is taken to be 0, therefore if any external particle enters or any neighborhood particle enters its region, the particle do not feel any extra force on it, or do not feel any extra interacting energy on it. Okay, so this particle will feel free here after entering. This is the case of ideal gas. In case of real gas, this particle will feel some force, because potential, if potential is non-zero, therefore there will be force will be what? Force will be non-zero. If force will be non-zero, therefore momentum will be what? Momentum will be non-zero. Okay, therefore there will be a momentum exchange between these two particles. This is not allowed in case of ideal gas. You have to remember this thing each and every time. So I am moving on. Let you have some particles. I am writing this thing here. Let we consider an assembly of n bosons, and these are distributed among energy levels. Okay, I am not writing energy levels, which has certain degeneracy. Okay, so let you have some energy levels. The data labeled as E1. This one is E1 energy level, this one is E2 energy level, this one is E3 energy level. Okay, E3 energy level, this is E4 energy level, and this energy level has degeneracy G1, G2, G3, G4. Okay, so among n particles, I am taking n1 particle and distributing on this thing, on this level, say E1, and among this n, I am taking n2 particle on the E2 level, and n3 particle on the E3 level, and n4 particles on the E4 level. So the total number of particles will be what? Total number of particles will be, say this is n, and n will be what? N I am giving first. To say if I have certain energy levels up to EI energy level is the last energy level. Okay, up to EI energy level. Yes. Therefore it will be what? N1 plus N2 plus N3 and dot 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 up to N. Suppose up to not, I'm not writing this thing as, say this is up to some certain value. Okay, say N P. Therefore what will be this value? This will be writing as summation Ni I equals to what? 1 to P, where P is what? P is number of energy states. Okay, number of energy levels. So this is the total number of particles. This is the total number of particles. Okay, now I am writing the let me write this thing. Okay, the distribution function in this case will be what? I think you know this thing. As these are bosons, the distribution function will be what? Given by, say, f of ei, where I ranges from 1 to t. Okay, f ei is equals to 1 upon, say this is e to the power alpha plus beta ei, and here is minus 1. So you can replace this distribution function by the number of particles upon the degeneracy, okay, on the ith energy state. So here it is e to the power alpha plus beta ei minus. This is the thing. So what will be the number of particles here? That will be ni equals to gi upon e to the power alpha plus beta ei minus 1. This is the number of particles in case of Bose-Einstein statistics. Okay, you have to remember this thing. Now I am going to the fact that let's take another parameter, say a, which is replaced by e to the power minus alpha. So what will be e to the power alpha? Alpha will be 1 upon a. Therefore, from our ni value, there will be ni. Okay, this is ni. And what is our value? Gi upon e to the power alpha times e to the power beta ei here will be, and there will be a minus 1 term. Remember this minus in case of Bose-Einstein statistics, and in case of Fermi-Dirac statistics you have to introduce a positive sign in the very middle of these two terms, okay, in the denominator. So now replace this e alpha with our newly introduced parameter, say a. This will be what? Gi equals to e to the power beta ei upon a. Just wait for a while. Okay, that's fine. Beta ei minus 1. This will be ni. Okay, this is what we call the ni. We know the number of particles cannot be negative. Number of particles is a positive number. Number of particles cannot be negative. Okay, the particles can be have some zero particles in a particular state, say ni, up to 0 to you can have infinity number of particles in a system. So what is the range of number of particles, or the span of number of particles is 0 to infinite. Okay, so to make this thing possible, so this is what this is. Let me change the ink. This is what this has to be higher than 1, otherwise the ny will be negative here. We don't want any kind of negativity in case of number of particles, because number of particles can range from 0 to infinity. So we can easily write this thing that e to the let me just wait, let me change this ink also. Say I'm taking another ink. So e to the power beta ei upon a minus 1 has to be very greater than 0. Okay, this term is the first term has to be very greater than 1, because we are dealing with a statistical system and we have to make this ni very higher. Okay, so we have to take this thing. Now what we can do from this thing, we can write this thing as e to the power minus beta ei upon a very greater than is 1. Remember this thing. Okay, if I'm writing this thing, just if ground state energy ei, say ei is ground state energy and ei is having value 0, therefore from this equation what we can write, e to the power 0 upon a very greater than 1. We are calculating this thing for the ground state energy levels. Okay, so what will become, it becomes 1 upon a is very greater than 1. So a will be what, a will be very less than 1. Okay, because there is a inverse relationship between 1 and 1 upon a. Okay, now I'm making a graph of this thing that a is very greater than 1. So what can be the value of a? A have to be in between. So a has to be in between 0 and infinity. Therefore there will be 0 greater than equal to a and greater than equal to 1, because the maximum value of a could be 1 in some particular situation. Okay, so I am taking what could be the maximum. As we know in case of ground state the value of a will be very greater than, very less than 1. But what can be the maximum value of a? The maximum value can be 1, but not more than 1. Okay, and what is the minimum value of a? Has to be 0. Why it is 0? Because in the term distribution function term, you can see, if you put 0 here, if you put 0 in this place of a, what does it become? This term becomes infinity. Okay, something by 0 means infinity, and infinity minus 1 means this denominator completely becomes infinity, and the number of particles becomes 0. Okay, number of particles can be 0. So here and if this is 1, if this is 1 and in ground state this is 0, therefore number of particles becomes 1. Let me clear this thing. Okay, we are taking the ground state for our simplicity purpose. Just take this thing, ground state. Okay, ground state means ei has to be 0, and for making, and we know the number of particles are what? N is greater than equal to say infinity, and less than equal to 0. Okay, n will be 0 when a, I am taking a, n will be 0 when n will be in the state, in this state. You have to remember this. Plot on the function that ni equals to what? From this function, ni equals to gi e to the power say e to the power beta ei upon a minus 1. This is our number of particles. Okay, so number of particles will be 0 when number of particles, this term is also 0, this term is arbitrarily 0 we have taken for the ground state. So what we have to make number of particles 0, you have to introduce here a 0 here. And in case of making the number of particles infinite in the ground state, you have to plot 1 in the place of a. You can check this thing from the graph. Okay, so this is the conjugate graph in between the number of particles and the extra parameter that we have introduced. This is a. Okay, so now just wait for a while. Okay, I am now plugging this thing, say a versus alpha graph. Okay, a versus alpha graph. What else are a? A graph. I am taking graph. Okay, I am drawing a graph as, see, this a is what? E to the power minus alpha versus alpha graph. Okay, e to the power minus alpha versus alpha graph. This graph will look like, what is e to the power alpha? This is a. And what is alpha? Alpha is a parameter. Say this is, in case of this graph, you can check this thing from the calculation that in this place we are taking a, in this place we are taking alpha. Okay, for alpha, when alpha is equals to 0, say in this place alpha equals to what? Alpha equals to 0. In the case of alpha equals to 0, what is the value of a? In case of alpha equals to 0, put this alpha 0 here. Alpha equals to 0, a has value 1. Okay, this is the 1 value of alpha, and there is a exponentially decreasing term, so there will be a graph. Just wait. There will be a graph like this, exponentially decreasing. And from this term, in the negative side of alpha, if alpha, put this alpha negative, therefore putting this alpha negative and 0, and this will look like this. Okay, this will look like this. This is the intersection point in between this. Check this thing. Okay, check this thing. So from the graph, what we can see in this place, say a is running towards 0. Okay, and in this place a is what? A is equals to 1. This is the maximum value of a, and this is the maximum value of minimum value of a. So we can see from the graph also that a is always greater than 0. Okay, and a has a maximum value, say a has a maximum value 1. From the graph it has been also been checked out. Okay, now physically taking the value of a, by some calculation. I am not giving the calculation. Okay, the alpha is treated as, say, alpha is equals to just wait for a while. Alpha is equals to mu upon kt. Therefore a will be what? A is equals to e to the power minus alpha. Therefore e to the power minus mu by kt. Okay, alpha is equals to, say, minus mu by kt. I think it is correct. So e to the power mu by kt will be here. Okay, now as we know, the maximum value of a is what? 1, and the minimum value of a is what? 0. Putting the value here, and so what we can say from this, that mu by that, just wait for a while. Therefore e to the power minus alpha is value in between 1 and 0. When the maximum value will happen for alpha value, maximum alpha value will be what? Maximum alpha value will be say 0, and the minimum alpha value will be what? Minimum alpha value will be, say, infinity. I think so. Minimum alpha value 0 to infinity. Okay, I am writing this thing in the conventional types. Alpha ranges from 0 to infinity. That means mu will be ranging from, I am writing this, mu upon kt is greater than equal to infinity, less than equal to 0, because alpha is what? Alpha is mu upon kt. Okay, when it will be, when if t tends to, you can check this thing, if t tends to infinity, there will be minimum value, say 0. This term will be vanished. Okay, therefore if t tends to 0, that means in the absolute 0 temperature, there will be a infinite term of this thing. Okay, infinite term of this thing. So this is, now I'm concluding this thing. Okay, for ground state, concluding this thing. For ground state, E is equals to 0, A is equals to what? 0 to 1, and for what? Alpha is equals to what? Alpha I am not writing infinite, alpha is, say, greater than equal to, sorry, just wait, alpha is greater than equal to 0. I think alpha is less than equal to 0. I think alpha is less than equal to 0, and mu will be what? Less than equal to 0. This is the chemical potential. Chemical potential will be 0 when mu will be 0 when the system is in equilibrium. Okay, equilibrium condition. Equilibrium means there are no transfer between number of particles are changing in between these two systems. Okay, if there are changing systems always, if there are exchanging particles from where up to the time when the particles are exchanging between two states, the mu will not equals to 0. Okay, and in case of the static case, say in case of equilibrium condition, the number of particles are fixed. In case of the particular systems, the mu has to be 0. Okay, this is, so now let's make an heading on the calculative part. And no, I'm making a separate video of this thing. Okay, I'll surely make a separate video of this thing. Up to this thing, end this video here, and on the very next video we'll be discussing on the the calculative part of this thing. Okay, the calculative, then in that part we'll discuss on, say, number of particles, say energy, say degeneracy. Okay, so up to this, thank you.